Hello, sixth period. You all get... Alright. You all get an additional recording because you guys were one class behind the rest of the classes, alright? So for this first lecture, we're going to talk about currents, okay? Alright, so what are currents? They're the continuous movement of seawater in a particular direction. And that continuous movement of seawater brings with it nutrients, dissolved gases, and heat, okay? The currents are created by wind. They are affected by the Coriolis effect. They are affected by temperature, salinity, and tides. Now remember, wind is going to move the water considerably. Last class that we were in together, where we were actually learning, you saw Garrett McNamara break the world record for surfing the largest wave, and you were told by me that that wave was created not only by the shape of the seabed, but by the wind. The wind was actually pushing that water, and so that is still true, right? So you see the effect that wind can have on water. So it should not be a surprise to you that this wind creates the surface currents that we see in our globe, all right? Now, when we talk about the water carrying nutrients, that's because of runoff, because of the change of the lower currents of water that come up towards the surface. They'll carry a lot of dissolved gases and nutrients with them. And then also the surface layer, that's where a lot of gases are dissolved, and as the water moves, the gas that is dissolved is moved with it, right? The heat that it carries usually comes from the equator, where we see more direct sunlight, and that direct sunlight heats up the water, and that heat will stay with the water as it moves up the sides of the continents, or as it moves down the sides of the continents, okay? And towards the poles, okay? All right, I want you to go to YouTube and watch one of these videos here. It's about the Coriolis effect. And if you don't want to watch these videos, just go to YouTube and kind of search the Coriolis effect, an explanation of it. And you should find the guy that does the crash course videos in chemistry, and he does a really great explanation of what the Coriolis effect is. It's a perceived effect, and it's a force that results from the Earth's rotation, and it causes objects or particles in motion to deflect to the right in the northern hemisphere and to the left in the southern hemisphere. So it is this clockwise or counterclockwise movement of an object based on the Earth's rotation. So as we throw something, although it seems as though we are stationary, we are still rotating as the Earth is moving. And so what we've thrown has a trajectory that bends according to where we're located. Right? And that's really what the Coriolis effect is. And it affects currents because of the spin of the Earth. So the spin of the Earth will affect the spin of the water that is on the Earth. It'll affect the particles that end up, the evaporated particles of the water that end up in the atmosphere. So it will affect the spin or the movement of these bodies of water or bodies of air. All right? Now, we have a ton of surface currents, as you can see here. These are all your surface currents. And these surface currents bring with them the nutrients, the dissolved gases, and the heats. And they kind of travel the entirety of the globe. So currents are usually called your global, they're global conveyor belts, really, where they just constantly bring and replenish nutrients and such based on their movement, okay? So your currents are going to be typically driven by the wind, most affected by the wind, because that's where the wind travels over. They are steady, they are dependable, they're not going to change direction. The global wind patterns are what cause this constant movement, and those patterns, the global wind patterns, are actually caused by the uneven heating of Earth's surface and land by the sun. Once you watch the second video, you're going to see my lecture on monsoons, and it'll give you a really great visual of this uneven heating of the land versus the sea, okay? Now, how do currents work? Well, pretty much, your water at the equator is hit almost directly by sunlight, right? So even though we are at an angle or we have a tilt, right? And near the equator, we have almost direct sunlight. And so excess heat deflected from the heating of the water is going to cause the air particles around the water to rise, right? They're going to cool as they rise, then they're going to sink, and it's going to create this convection current of air. In the northern hemisphere, they tend to have a clockwise spiral, and in the southern hemisphere, they'll have a counterclockwise spiral. But there's always going to be a circular movement of this cooling and heating pattern, right, to these convection currents. This creates boundary currents, which are dynamic and determined by the presence of the coastline, and they fall in two distinct categories. So you have western or eastern boundary currents. And eastern boundary currents are usually found on the western side of coasts, and western boundary currents are found on the eastern side of coasts. Now, eastern boundary currents are usually shallow, they are broad, and they are slow flowing. They are found on the eastern side of ocean basins adjacent to the western coasts of continents. So in normal people words, they are found on the west side of continents. So they'll always be, if you're on the west coast, you have an east coast boundary, or excuse me, an east coast boundary current. If you are on the east coast, you have a west coast boundary current, okay? Eastern boundary currents usually flow towards the equator. They transport cold water from higher latitudes to lower latitudes, meaning that they move from the poles towards the equator, right? Now, eastern boundary currents are the following, but what I want to show you is the visual here. So your eastern boundary currents usually move towards the equator, right? And so then you have an equatorial current, and then you'll have a western boundary current, and so on, all right? Here we have we're on the east coast, so our western boundary current, Gulf Stream, moving up towards the poles where the water is cooled, and then it flows back down towards the equator, and this is an eastern boundary current right here, okay? Now, if we move on to western boundary currents, these are warm, they're deep, they're narrow, they move quickly. The water is heated quickly, they move very fast, okay? They form on the west side of ocean basins due to western intensification, which is this is related to gyres or large spiraling wind currents over the water, and that's caused by the Coriolis effect, all right? They carry warm water from the tropics towards the poles. So again, warm water from the tropics up towards the poles. And you have heavy gusts of wind that help to carry that. They're fast. It says they're deep currents. The reason for that is because the surface area and the areas below it get heated really quickly. And that heat transfers and dissipates into the surrounding area, creates that strong thermocline, and so you have a really deep container of warm water barreling upwards, okay? And then this just shows a little bit blurry version of your moving currents, okay? All right, so currents, your deep currents. Deep currents are, or thermohaline circulation, is driven by the differences in densities of water caused by temperature and salinity, right? Thermal temperature, haline, salinity, circulation. Okay, these usually happen closer to the ocean floor, and this is often called the global conveyor belt because it carries a huge amount of water that has a lot of nutrients and dissolved gases in it. But it moves constantly around the globe, so replacing water constantly, okay? Now, it starts off in the North Pole where the cold water will freeze or is near freezing. As this fresh water freezes into ice, what's left is the salt, and the salt will sink into the water below. That movement, that sinking of the salt actually creates movement within the water, right? So this makes cool, dense water down well or sink towards the bottom. The descending water creates that movement and a slight mixing in the water column. And then the deep water moves through the Atlantic Ocean towards Antarctica. Once it's in Antarctica, it picks up even more cool water. It'll start to split at that point. One part of the water moves towards the Indian Ocean, while the other moves towards the Pacific Ocean. In the Indian Ocean, the deep waters move towards the equator, right? And then you'll see as it's moving towards the equator, a lot of that cool water starts to come up to the surface, all right? It brings nutrients with it to the African coast. The water begins to warm as it nears the equator, it rises, and then it joins the warm surface currents. In the Pacific, the water moves towards the equator as well. As it warms, it rises again. It becomes part of the surface current, carrying the nutrients to the west coast of the U.S. So again, as it starts to move up in these areas where you see that there's purple, where the cool water is joining the surface layers, right? As it starts to move upwards, you see that a lot of areas near there will have higher productivity because there's a lot of nutrients coming to the surface, right? If organisms there don't use up those nutrients, and as that water travels along the surface, any producer that can utilize those nutrients definitely will. Okay? And that's that.